Hi Math 3 students, and welcome to your 3.7 Ed Puzzle. So let's go ahead, start off by reading. It says, when working with quadratic functions, we learn that the fundamental theorem of algebra is that an nth root polynomial function has n roots. In this task, we will be exploring this idea further with other polynomial functions. First, let's brush up on what we learned about quadratics. The equations and graphs of 4 different quadratic equations are given below. Find the roots for each and identify whether the roots are real or imaginary. So if we're looking here, let's go ahead and look at number 1. So first off, let's go back to our rule here. It says an nth degree polynomial function has n roots, okay? So all polynomials are going to be degree 2, okay? Because they have that x squared in there. So according to the fundamental theorem of algebra, each of these polynomials should have 2 roots, right? Because an nth degree polynomial has n roots. If it's a second degree, it should have 2 roots. So let's go ahead and look at number 1. All right. First we got to find the roots. So there's 2 ways to find roots. If you have the function, you can just look at it, see where it crosses the x-axis. All right. So it crosses the x-axis here, at -3 and 2. All right. Another way to find the roots is to factor and set equal to 0. So we did practice factoring. So we got x plus 3 and x minus 2. How did I get this? We got to figure out what multiplies to give us a -6 and adds to give us a 1. That's going to be a +3 and -2. We're going to set each of those equal to 0. We get x equals -3 and x equals 2. All right, so the roots here would be x equals -3 and 2. And then the type of roots. So what they mean by that is last year we talked about real roots and imaginary roots. All right, in this case, we have 2 real roots because they do go through this x-axis. If they go through that x-axis, they're going to be real roots. So we'll say 2 real roots. All right, now let's go ahead and try B. So now B is a little bit trickier, right? If we look at B, you see how these don't go through very nice points, right? I can't look at that and tell you exactly what point that goes through. Then we could look to see if we can factor this. This is actually prime. We cannot factor this. If we try and figure out what multiplies to give us a -7 and adds to give us a -2, we will find nothing. All right. So one thing we can do here is use the quadratic formula. All right, so we have -b plus or minus square root of b squared minus 4ac all over 2a. All right, so let's go ahead. We've got ax squared plus bx plus c. Hopefully this looks familiar to you. So our b is a -2, so -b is going to be +2, plus or minus. Our b squared is 4 minus 4 times a, which is 1, times c, which is -7. Then we do 2a, which is just going to be a 2. And then let's see, within our root here, we are going to end up with 4 plus 28. All right. So we got 2 plus or minus 2, and then we can simplify that. So we get 2 plus or minus, and then that ends up being root 32 all over 2. And then if we try and simplify that, 32 is 16 times 2. So we can take that 16 out and it becomes a 4. So you get 2 plus or minus 4 root 2 all over 2. So this ends up simplifying to 1 plus or minus 2 root 2. So that was quite the problem there. But essentially, we just use quadratic formula. All right, so our roots here are going to be x equals 1 plus or minus 2 root 2. So that would be your roots. And the type of roots are 2 real, right? Those actually go through the x-axis. So we've got 2 real roots. All right, now let's go ahead and try C. So if we look here, you can see that this is definitely a root there. So we've got 2 as a root, right? So the root would be x equals 2. Now, again, you could find this by factoring. So we could factor this guy out, and we get x minus 2 We set this equal to 0. We end up with x equals 2 and x equals 2. Notice how we got the same solution twice. All right? So what actually ends up happening if you write this if you recall vertex form, right, you get x minus 2 squared. And essentially what you have here is a duplicity, okay? So your answer here is we have one real root, but it has a multiplicity of 2. All right, notice how I got the same solution twice. All right, if you get the same solution twice by the factors, you will end up with something with a multiplicity of 2. So really, if you look at it, it looks like there's only one root, but it has that multiplicity of 2, so hence it does have 2 roots. All right, so last one here. So if we're looking at D, well, here's my x-axis. Notice how this parabola does not go through the x-axis. Hence, there are no real roots, right? But we can find the roots by using the quadratic formula. All right, so again, the quadratic formula is negative b plus or minus square root of b squared minus 4ac all over 2a. All right, so we are going to end up with 4 plus or minus 16 minus 4 times 1 times 5. All right, so we end up with, oh, and that's all over, sorry, 2a. I forgot about that. All right, so then we end up with 4 plus or minus 16 minus 20 all over 2. And then you end up with 4 plus or minus root negative 4 all over 2. So now this here, hopefully you guys remember what you do when you have the square root of a negative number. You get an imaginary number, right? Square root of negative 4 is actually 2i, right? So the answer here would be 4 plus or minus 2i, 2. How did I get the I? If you guys remember imaginary numbers, the square root of negative 1 gives you I. So if you have negative 4, it's going to be negative 1 times 4. Well, we know that root 4 is 2, root negative 1 is I, we get 2i. All right, then you can simplify that. That's going to become 2 plus or minus I. All right, so the roots here would be x equals 2 plus or, oops, I can make that a little bit bigger, 2 plus or minus I. And then the type of root, well, these are two imaginary roots. All right. All right, so for number 2, the question asks, did all of the quadratic functions have 2 roots as predicted by the fundamental theorem of algebra? Explain. So let's go ahead and look back at these quadratic equations. Did all of these guys have 2 roots? And to answer that question, yes, they actually did. This guy had 2 real roots. This guy had 2 real roots. They were gross roots, but they were real. This guy had 1 real root, but it had a multiplicity of 2. And then this guy had 2 imaginary roots. So to answer this question, yes. Even though C had 1 root, but with a multiplicity of 2. So even though C had 1 root, it had a multiplicity of 2. And it says it's always important to keep what you've previously learned in your mathematical bag of tricks so that you can pull it out when you need it. What strategies did you use to find the roots of the quadratic equations? Now, this is actually a super helpful question, and I actually think like this should be like memorized. You should know this. You should have this in your back pocket because these quadratic questions, these quadratic problems are all over the SAT. And the SAT isn't going to tell you, oh, you need to, factor this. Oh, you need to complete the square. Oh, you need to use quadratic formula. You are the one who has to kind of decide what you're going to use. So let's write out all the different ways that we are able to find the roots of a quadratic. So one way is by factoring. Right, you factor the quadratic, set it equal to 0. Another way is completing the square. Another way is using the quadratic formula. And then the other way is by looking at the roots on the graph. Personally, my first one I would go to, if I had a graph, I would use this guy. This would be my first choice. I would look at the roots on the graph. If I didn't have a graph, or let's say the roots weren't nice, right? If you look here, the roots aren't very nice. You can't use that method. For one, you were able to just look at it and get the roots, but for number two, you couldn't. So I would try, looking at the graph first. If that didn't work, I would definitely try factoring. If factoring didn't work, I would try completing the square. If factoring didn't work, I would use the quadratic formula. If that didn't work, then I would complete the square. That's kind of the order I would go in personally as a mathy person. Number 4 asks, using your work from problem 1, write each of the quadratic equations in factored form. When you finish, check your answers by graphing, when possible, and make any corrections necessary. So they want us to put this into factored form. So first off, let's just think about what the roots were. Let's say I only gave you the roots, right? And if we look back here, our roots were -3 and 2. So if we wanted to put this into factored form, we would do x minus -3 and x minus 2. So we end up with x plus 3 and x minus 2 would be your answer there. So notice how I did that. It was like x minus a root, x minus root 1, x minus root 2, right? So if it's negative, it becomes positive. If it's positive, it becomes negative, all right? So then for the next one, all right, we're going to go ahead. We know that our roots, if we look back up, were 1 plus or minus 2 root 2. All right, so if we wanted to put that into factor form, we're going to do x minus 1 plus 2 root 2 and x minus 1 minus 2 root 2. So you end up with something like that. So then what you end up having to do here is distribute this negative to each of these terms. So you get x minus 1 minus 2 root 2. And x minus 1 plus 2 root 2. So those would be your that would be your factored form. All right. Then for C, we got 2 roots, right? Well, it was one root, I guess, with a multiplicity of 2. So we had x equals 2, if you recall. That was our root there. So the factored form of this, since it has a multiplicity of 2, you're going to do a square. Now you're going to find out, sometimes you might be told it's a multiplicity of 3, a multiplicity of 4. If it was a multiplicity of 3, it'd be 3. If it's a multiplicity of 4, it would be 4. So the multiplicity tells you the power. Since it's a power of 2, you put a 2 there. Then for the factored form, for D, our roots were x equals 2 plus or minus I. All right, so we're again going to do x minus our roots. So we're going to do x minus 2 plus I and x minus 2 minus I. So we end up with x minus 2 minus I and x, oh, I forgot to put this in parentheses. Sorry, guys. And x minus 2 plus I. And that would be your factored form. All right. So then it says, based on your work in problem 1, would you say that roots are the same as x-intercepts? And in this case, if the roots are real, then yes, they are the x-intercepts. Okay? So if the roots are real, then yes, roots equal the x-intercepts. All right? And then based on your work in problem 4, what is the relationship between roots and factors? All right? So if a root is x equals a, oops, then x minus a is a factor. So on the next page, it says, now let's take a closer look at cubic functions. We've worked with transformations of x cubed, but what we've seen so far, that's just the tip of the iceberg. All right. So it says, for instance, let's consider this function. We got x cubed minus 3x squared minus 10x. So number 7 says, use the graph to find the roots of the cubic function. Use the equation to verify that you are correct. Show how you have verified each root. All right, so first off, think about the different ways that we said we were able to come up with the roots, right, when we wrote out all those options. One way is just by looking at the roots on the graph. And that's actually quite helpful. So let's go ahead and look at the roots on the graph here. Well, it goes through -2, it goes through 0, and it goes through 5. All right, so we can say our roots are -2, 0, and 5. All right, then it says write G in factored form. Verify that the factored form is equivalent to the standard form. Okay, so this is super important. So first it says write it in factored form. Now let's hop back to here. It says what is the relationship between roots and factors? Well, if we have a root, we can just do x minus our root, and then that is now a factor. So let's go ahead and do that. We're going to do x minus -2, x minus 0, and x minus 5. So this guy becomes x plus 2. This guy just becomes an x, and this guy becomes an x minus 5. So now they want us to go ahead and multiply this out. They want us to prove that this is equivalent to the standard form of this. All right. So what I'm going to do is I'm going to kind of rearrange them and put these two binomials next to each other. And they want us to show that this is equivalent to this. So how I'm going to do that is I'm going to first FOIL out these two binomials. So I'm going to keep my x out in front, and I get x squared minus 5x plus 2x minus 10. Combine like terms. I get x squared minus 3x, minus 10. And then we can go ahead and distribute this x. We get x cubed minus 3x squared minus 10x. Notice how this standard form matches this exactly. We just came up with that by looking at the graph, which is kind of cool. So kind of the two answers to this, to number 8, which would be our factored form, right? And then we verified by getting this into standard form. All right. And it says, are the results you found in number 7 consistent with the fundamental theorem of algebra? So let's look back. Well, what is the fundamental theorem of algebra? And that is that an nth degree polynomial has n roots. Okay. Well, let's look. What degree polynomial is this? And recall, to find the degree of a polynomial, you look at the highest power. That's a 3. So it's a degree 3, which means that it should have 3 roots. And guess what? It did. Degree 3, we had 3 roots.